It's on? Yes. So this is a tutorial that a friend of mine for many years, Mazen Gilbert, who's an AT&T research, and I gave back an inner speech 2010. And the title was Mobile Voice Search. So when Jose Luis contacted me about this, and he suggested this topic, because, okay, I can talk about that, but I can also talk about a bunch of other things. And I didn't know exactly the audience. That's why we spent most of the time on the other topics, which hopefully you found useful too. But maybe I can spend some time talking about this. And the idea is, how many of you have used voice search in your smartphones? Raise your hand. Like a small number of them. In the United States, at least, it's getting quite popular. So people are getting interested in saying, okay, so how does that work? So this talks about things along those lines. And we're not going to have this a 3-hour tutorial, so obviously no way we're going to cover it in 45 minutes. So I will just selectively sample a few slides that I think might be useful. So forgive me if I skip some of them. We took quite a bit of time to prepare this. These are all the people from AT&T and MSR that helped us prepare. This contains some of the history of spoken language technology. I guess one of the things that I remember interesting is the Mechanical Turk. How many people know about Mechanical Turk? Amazon Mechanical Turk? Most people, right? Obviously, right? So many of you probably have been Turkers. The original name of Mechanical Turk came, you know the original person? I mean, is this chess player. So this machine in the 1700s that you brought and said, well, this can play chess and beat you. And it's a machine that was winning. So, man, this guy is doing, they didn't even know what artificial intelligence was back then, okay? But it was artificial intelligence, except there was a little catch. It's a big box, and there was a little guy underneath that was moving the pieces, right? So that's Mechanical Turk. Because the reason why it was Turk is because it was making look like it was playing with a Turkish, playing with a turban. So it was like a Turk, but it was mechanical. But it's not really mechanical. Anyway, so there is like something similar with a speech synthesizer and lots of activities. I won't go into this. Let's see.
Would you please make the voter say for our Eastern listeners, good evening, radio audience. We're just really beginning to understand the capabilities of the computer. Can machines really think? Well, I think you better even a scientist. And I don't think my daughter will ever marry a computer. But I think the computers will be doing the things that men do when we say they're thinking.
Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
Let us now look at the performance of the system in a couple of other task domains: news retrieval and medical diagnosis.
Tell me about war.
Remember when you used to call the airline and tell them where you wanted to go?
Thank you. To continue, please push 1 now. Thank you. If you know which buttons to push, there's no need to listen to the end of each message.
I could walk home in the time it takes me to get that information.
8.500 pesetas con la comisión del 2% son $87.
8,500 pesetas with the commission of 2% comes to $87.
Here's $87.
You have a lecture at 4:15 on deforestation in the Amazon rainforest.
Right. Let me see the lecture notes from last semester.
Good morning, America. And good morning, Joan.
Casper, schedule a meeting with Bob Straw.
What day would you like to meet?
AT&T, how may I help you?
Calpe esta al 993
910-3440.
Do you want to place a call and charge it to a third number?
Would you like to request a kosher meal?
No, not really.
Okay. That is all I need for your registration. May I help you with anything else?
Send a message to Scott. And a new email is created, ready for me to fill out and click send.
Shelton West Village. I'm here.
AC on. CD play, disc 4. Find nearest Chinese restaurant.
Hello, and welcome to Movie Phone. If you know the name of the movie you'd like to see, press 1. Using your touch-tone keypad, please enter the first 3 letters of the movie title now. Why don't you just tell me where you want to see the movie?
This is where you want to have emotion recognition. That Kramer guy is priceless. I mean, that face, I mean, you have to be an actor, but it's like that's what everyone loves. He didn't say anything, just because he's totally puzzled. Like, what the heck is going on? So there's what you want, emotion recognition. So this is a whirlwind tour of the technology since back of 1939 in AT&T's demonstration in the World Fair in New York, where it was saying, "Good morning, radio audience," and the speech synthesizer. So it's changed a lot, obviously. Sometimes I tend to talk to my colleagues that think we improve 10% accuracy a year. Well, on a given year, the improvements are not that much. But if you put it in context here, we have made quite a bit of, the community has made a lot of progress in all these decades. So this is a little bit of historical perspective. Evolution of voice services. Like a lot of the work in speech recognition in the early days was based on AT&T Bell Labs. And because they were the phone company, all they did is work on, so well, the assumption is you're holding something like this and you're talking to a system instead of a person. What can you do? So the traditional voice calls, then it came with directed dialogue, then it went to natural dialogue. How can I help you? And then it came to mobile search, where you have a phone that is more than just a microphone and a speaker. It has a screen and touch capabilities for input that you can do a lot of other things. But this is kind of new. Most of the speech research was done by just assuming that all you have is a dumb phone that doesn't have any keys or anything beyond that. So I think I have a few voice clips here.
This is AT&T. Please say, collect, calling card, third number, person to person.
I'd like to make this a collect call, please.
Thank you. Please hold for billing acceptance.
So this is an example of command and control, where the system is just trying to see if you're trying to place a collect call. I don't know how many of you even know what that is, because this is from the days where you would go to a payphone in the street. Remember those? Like I know there are very few these days, because why you want a payphone if I have my cell phone? So in fact, I was trying to describe a few kids what a payphone was. It's like, what is that? Why do you want to go? Couldn't you just use your cell phone? So, well, son, cell phones have not been around for that long. So back then, you pick up the phone and you could say whether you want to pay for the call if you put the quarters in the machine, or if you want someone to pay for it at the end. You're like stuck and you want your parents to pay for the call, and they would be glad to do that. So those are in the old days. Then there are more advanced systems that can do more.
AT&T. I am an AT&T automated assistant. You can speak naturally to me. How may I help you?
I want to question a telephone bill that I just received.
Okay. What is your question?
What's my question? I get billed every month, and I pay every month right when I get the bill. But this month, I've got
outside calls for August, September, October. I mean, weren't they on the other bills?
I can explain that to you. Some customers are receiving a bill that covers more than 1 month of AT&T charges. If your long-distance charges are under $30 per month, you will not be billed every month. Is there anything else I can help you with today?
Okay, so she was happy, I guess. So these are the kind of things that the community was working on when the assumption is that you didn't have anything other than just a regular telephone. So one of the applications that became of a lot of interest to researchers in the field was what we call 411. At least that's the number that you call in the United States when you want to direct your assistance. By the way, there is a longer history. In the old days, when the telephone first arrived, there was the operator. Remember? Pick up the phone. There was like these wooden kind of things that you put here and say, operator, operator. Say, okay, I want to talk to the grocery store. So, oh, you mean you want to talk to Jane in the grocery store? Yes. The operator in the town knew the names of all the businesses. In fact, if you wanted to know the gossip too, you could call the operator and because she was routing all the calls from everyone in the little town. So she knew everything that was going on. So that was the operator back then. Then you have the new systems like that. And well, now you need to automate it because it would be too expensive to have a person route the calls. But sometimes you don't know, you just want to find some business that you want to call, but you don't know the phone number. Of course, you have the thick phone book. Remember those? You still have some of those? Now you just go to the web and look it up, right? But in the old days, there was something that was helpful to find out the name of the business, or you could use as paperweight sometimes. Depends on, it's really thick, thousands of pages. So occasionally people would still call and say, well, I'd like to know where the nearest McDonald's is. And they would call the operator. And this was the 411 service. It used to be free. Before 1984, AT&T had a monopoly in the United States. So they were charging high enough rates that they would say, well, we'll give that service for free. So you could just call, and people got used to it. I don't think that was necessarily true in other parts of the world, but that's what happened. But then after competition came and they lowered the prices, well, it was expensive to have humans answer all these calls. So it made sense to consider, can we automate that? A lot of the times people just ask a question, where's the nearest McDonald's? So well, here it is. Can we automate that and reduce the need for operators? So since 1984, if you want to make one of those calls, you have to pay. I mean, you'll see $1.25 in many cases for each of the calls where you request assistance. So probably only if you couldn't do it because you're traveling somewhere and you don't have the thick phone book or that's not helpful, you would call, but some people do it. There was a company called TellMe, which ended up being acquired by Microsoft years later, that in 2003 automated a fraction of them. So made a deal with AT&T and Verizon and other companies where whenever someone calls, they would automate a fraction. And they have a confidence score so that if the system thinks, I'm pretty sure, this is what I heard, that that's right, it would automate the call. And if it wasn't sure, that doesn't mean maybe it got it right, but it wasn't sure, the confidence score was not high enough, pass it to a human operator. So all it did is automated a fraction, but that was still helpful. That was still millions of dollars that you could be saving by doing this. Later on, back in 2005, in the US, there was something called Free 411, which was ad supported. The reason why they make money is they gave the name of the business. So if you say McDonald's, did you say McDonald's? Yes, here's the name, it's McDonald's. By the way, are you interested in Burger King? They offer tasty burgers. So that's how they made money, right? Later, the search engines in 2007 announced Bing 411, Google 411, that did something similar. And just because search engines make their money with ads as well. Although those ones have no ads. This was just to develop the technology. So in smartphones have changed all this. In fact, this is one of the examples that I was mentioning earlier, where at first we thought, oh, that's going to be the solution. Well, guess what? There was a new way of solving the user's problems. Now the smartphone has this keypad, and you can type and search pretty good. So why do you need to speak? And that was another hurdle. There are other ways of doing the same problem. So you cannot just say this one works. Well, this one works and is better in some sense than the alternatives. And many people, you use your smartphone, you just type what you want and you get good results. By the way, this reminds me of an anecdote. I worked for 2 years in the R&D labs of Telefónica, the Spanish phone company, Telefónica y Más D. And one of the things that was very exciting is that when I was in the back room talking to one of my colleagues that worked in fixing the network switches. The switches is the thing that connects one color with another, kind of like the router in the internet world. So he told me, oh, we need to maintain switches because they're expensive equipments for many, many years. And in fact, he took me to one of the older switches that was built in the 50s. And it was unbelievable. You come in, and it's so loud. You hear all the relays clicking. This was not transistors. This was relays. And do you know how the technicians fixed, because these things would fall, they would break, how they would fix it? With toothpicks. They would go and say, well, this relay is not clacking. I'll put a toothpick, and now it will work for another year or so. So this is low-tech operation. Anyway, so with smartphones, people get this voice search, this information differently. So you need to reinvent. Speech could still be helpful, but it needs to be really accurate, faster than you can type, which you can type and make a lot of mistakes when you're typing, right? So it's possible. And it needs to be fast. If it's not both, then many people won't use it. This is an example of one of the first systems. In fact, we developed this as a prototype. At that point, it wasn't called Bing. It was called Live Search, which is a weird name. But the idea here is that you can use both voice as input and mostly visuals as output. An image is worth 1,000 words. You hear that? So why cannot do that if you have a screen like that?
Hi, my name is Rob Chambers. I work here at Microsoft Corporation, and I'm excited to show you a new feature of the Live Search for Windows mobile application. That feature is speech recognition. As you can see, I have the Live Search application running here on my phone, and my location is currently set to Redmond, Washington. Now, I can go ahead and speak or type a business name. Speaking is a lot easier than typing on these small keyboards on mobile phones today. Let me show you what that would be like. I can simply press the speak key and say the name of the business I'm looking for. For example, Microsoft. The system will think about what I said, come back with what it thinks I said. There it is on the screen, Microsoft. I got it 100% right. I'll go ahead and select that item, and you'll see the business search results right there on the screen. Coming back to the home screen, I can also set the location just as easily with speech recognition. For example, I can say Bellefontaine, Ohio. System clarifies with me, did you say Bellefontaine, Ohio? I did. I go ahead and select OK, and it sets the location right there on the home page for me. Just that easy. Now, one of the coolest things I get to show you is combining both of those operations into a single statement. I get to say just one thing, and that's going to contain both the business name and the city and state I'm looking for. Let's just see what that looks like. Cheeseburger in Paradise near Honolulu, Hawaii. The system will think about what I said. First, it's going to clarify the location. Did I say this location? Indeed, I did. Then it's going to ask me, is this the business name I wanted? Yes, it is. I go ahead and click OK. And now I get to see the business results. In one statement, the user will get to say anything that they want for any business anywhere in the United States in a single statement. That's really quite amazing if you think about it. Okay, well, hopefully I've given you a good flavor for what you can do with the speech recognition feature in the Live Search for Windows mobile application. Go ahead and download this up at wls.live.com from your Pocket Internet Explorer in your Windows Mobile 5 or Windows Mobile 6 phone. Thanks a lot. Bye-bye.
So this is another example where we got so excited that we could do this. And that one of the features there is useless today because most smartphones have location capabilities. So you need to tell where you are. The system knows. In fact, it knows not just Honolulu, Hawaii. It knows exactly where in Honolulu, Hawaii you are. So this is an area where you could do your PhD thesis on recognizing locations through speech. And that's good for like 3 years until it says, well, I just use my GPS chip. So, you know, that's the trade-off, right? No longer useful. I mean, of course, that was interesting. We learned a bunch of things. But the other question is, I've been in this place. They have good burgers if you like them. Let me see if I can, well. I'll give you the outline of how these systems, the block diagram of how these systems work. You can either type your query, and again, this will look interesting to you that you're all using search engines, and there is some natural language understanding. I'll go into more detail later. And you get information retrieval, and you get all of the search results. Or you could speak it. Nearest pizza restaurant. And it knows what nearest means, because now it has the GPS chip, the location, through recognition, and it tells you, well, this is the restaurant. So that's a very high-level view of one of these systems. Let me talk about the information retrieval component, because even though information retrieval, we tend to think that is just for the text search engines. A lot of the voice search algorithms are actually using this. This is what you get if you type, say, search engines. This is what you get in Google. You get something similar in Bing. And how does this work? Well, you have the web index. So a crawler has gone through all of the websites, they're just jumping from one to the other, and he gets all the pages. Actually, not all of them, but a lot of them. It's like billions and billions, 100, a trillion pages. And then there's a search engine that, if you think about it, is striking. It has to see, let me take this query and look in all the 100 billion web pages that the web has, and I'll tell you, first of all, where this text appears, number one. Second, of the many, many pages that will contain those two words, which are the most interesting to you? That's a pretty tricky problem. Again, going back to history, I just joined Microsoft Research in 1994. In 1995 is when the web started to take off. There was the Netscape Navigator that will allow you to see HTML pages. That was like a big thing. Even though we have been using FTP and Finger and other internet protocols, that was like HTML was a big deal. And the next thing is like, wow, but even the web was a lot smaller back then. It was already hard to keep track of what was going on. And one day, one guy comes, come here, let me show you this thing, search engine. I said, what do you mean search engine? And I saw a demo of Alta Vista. And I don't know if you know even what Alta Vista is, but it was the first commercially available search engine. It was built by DEC, Digital Equipment Corporation. Essentially, the problem, once you think about it, it's very interesting mathematically, but it was daunting. Now, how can you search that many web pages in milliseconds? The approach is what they call the 10 blue links. You find the URL, the web page, that contains that, and you rank them somehow. So a lot of these technologies are based on something called TF-IDF. So let me explain what TF means and IDF briefly, and you will see why this is useful not just for text, but also for speech. TF starts for term frequency, and essentially measures the relative frequency of a term. They use the word term, but it's actually like a word. Term I in document J. So let's say that my corpora, is just to make it simple, contains only 3 web pages. Very simple web, okay? And this is my document, or my documents. And this is, each web page is very small, just 1 sentence. This is, again, toy example. How will we do the term frequency? So here we see, for document 1, we have 5 terms. The word information, retrieval, is, good, powerful. These are all the words that are present in all the documents. So I have my vocabulary list. And I want to see in document 1, there is 4 words. So information accounts for 25%. That's the relative frequency. Retrieval, all of them, except for good. The word good is not there, so it has 0%. In document 2, there are 3 words, so you'll see thirds. And the word retrieval is not there, so it has 0. And the word powerful is not there. But the other ones, information is good. They have, this is the relative, the term frequency. Document 3 is this. So this is kind of like what the term frequency, the TF component will do. Pretty straightforward. Now we have IDF. We said TF-IDF is, TF is term frequency, IDF is inverse document frequency. And essentially it's a hack. The first time I heard this, I like all these principal algorithms, I was totally disgusted because this is a hack. Inverse document frequency, not quite. It's a heuristic that tells me how discriminative each term is. For example, the way it's computed is this is one of the possible implementations. M is the total number of documents, and MI is the number of documents that contain that term. So in this case, these are all the terms, and we see the IDF component for information is the number of documents is 3, and the number of documents that contain 2, 1, 3, 2, and 2. So what this tells you here is the word retrieval, the term retrieval, has the highest IDF of all of them. Meaning, if I know that keyword, it's going to be the most helpful in discriminating which document it is, because it only happens in one of them. If you use the word is, that word has no value at all, because it happens in all 3 documents, so it doesn't help me figure out which document it is. It doesn't have any discriminating power. So the IDF term is 0. And all the other words, information, good and powerful, they're equally helpful in discriminating. There are 2. It will help you get rid of one of them, but there are still 2 that you don't know. So those are the IDF values. So TF-IDF, what you do is multiply the TF component by the IDF component, and you get a matrix that looks like that. So this is a baby example, but in fact, that's how the traditional baseline search engine works. You have all the words here. It won't be 5 in a search engine. You'll have millions of these words, because even the misspelled version of a word still a term. Documents is not 3. It's, as I say, hundreds of billions. So you have a huge, huge, huge matrix. And you need to pre-compute it and store it. So, of course, there is the issue of how do you store a matrix that gigantic. And the answer is not stored. Most of the items are 0. So you don't store it with things that are mostly 0, because it's very sparse. So there are other mechanisms and tricks to store a very sparse matrix, mostly as a linked list. You sort this from the biggest to the smallest, and you store it as a list. And that's much more economical. Still, you need to have many machines to host it. And it's sorted by their TF-IDF scores. So the key here, why is it so fast? Because it's doing an inverted index. Meaning, if you type the word information, I go here and retrieve this row that is sorted. So it tells me that document 2 is the most likely one based on the TF-IDF value. So this will appear first, and this will appear second. That's how you re-rank. And because this is just a table lookup, it's very fast. So you do the inverted index, basically. If you type 2 words like this, it just adds the scores. I mean, it needs to merge, let's say, information retrieval. It will merge this list with this list. So you need to add these 2. And in this case, this D1, that was, if you only use the word information, it will be rank number 2. Because you have this one, it will be ranked number 1. So you flip the ranking. This is another way of saying the inverted index. You search for the terms. You've pre-computed this ahead of time, and now you can very quickly. That's why you can search billions and billions of web pages in milliseconds, because you do this inverted trick. Otherwise, if you were to do a linear search, forget it, right? So for those of you that are familiar with databases, this is kind of like a hash in a sense. So document retrieval, what people tend to do is the cosine similarity. Maybe you have heard about this cosine similarity. Is developing the query and the document as vectors, and you find the angle, which is the dot products in the Euclidean space, and that's how you compute it. One important contribution through addition to the basic algorithm that I described was developed by Larry Page, one of the founders of Google, in 1998. And it's called the page rank algorithm. By the way, this page is not like the guy was just wanted to put his name in the algorithm. He was referring to web page, okay? It's just a coincidence. That's what he claims. The basic idea is that the importance of a page, so some pages are more important than others. So even if the two words match equally well, some pages should be ranked higher because they are more important. Why is it a page more important than others? Well, one way to do that is if many pages point to that page, linked to that page, that's a feature that indicates that that page is more important. And this is what the page rank algorithm is doing. It's finding the solution to an eigenvalue problem. You have this big matrix, you invert it, and that can tell you if many pages are pointing to this one, this is more important, and it will get ranked higher. That's the basic idea. Okay, so I'm going to skip this and look at. So why is this useful? So let me show you a video. This is how a lot of speech voice search systems work. You have the waveform, you go through a recognizer, and it generates some text. And that text goes through a search engine. That's why you need to use something like TF-IDF. You could use a decouple approach, where you just send to the text search engine and see what happens. And in some cases, that's what the systems today do. But if you know how this works, you may be able to do a better end-to-end optimization. That's why I mentioned a little bit about TF-IDF. This is a case where you're not using the technology for searching businesses, but rather for doing something very different.
Is Project Natal the next version of Xbox 720?
This is you're trying to look into a manual.
The game Halo work with Project Natal.
So this, imagine these are kind of web pages. But this is kind of like searching in a manual.
I want to learn more about Project Natal. When can I buy Project Natal?
Okay, so let's see. What else I could tell you? I will show you some of the demos, which I think you may find some more interesting. This, I covered some of that already. Okay. So you could use this recognition, kind of a dictation model followed by search approach in many approaches beyond voice search. So let's imagine that you want to build speech recognition systems that would detect, let's say you're driving. This was developed, one of the first versions, in something called Ford Sync, which I don't think they sell in Europe, but it was very popular in the United States. This is a system that Ford Motor Company started selling that was integrated, and it had speech recognition built in. And in fact, it was so popular that a few years ago when they started selling it, there was the recession hit, and General Motors and Chrysler, the other two big competitors in the United States, went bankrupt. And Ford survived partly because of this system. It turns out that when users went to buy a car, if the car was equally equipped, same color, same leather, not leather, whatever, and one had sync and the other one didn't, the one that had sync sold much more quickly. So that was really successful for them. One of the things that you could do is have a menu tree. So things like that. And you could build a context-free grammar, just a very simple thing. And they're easy to write, but they're fragile. Here there is an example showing that if you build context-free grammars like this, it will work for a user that knows exactly what they can say. But if they don't know exactly what they can say, it falls apart. This is an example. Oh, let me play that again, I think.
Turn-by-turn directions. Business search.
Business search.
So those are examples where the user did not say exactly this. They said business search. Well, the system is trying to match a grammar that matches exactly this. Or the directions. Stumbles, hesitates a little bit. It will also increase the misrecognition. So those are fragile. So we developed a new mechanism for force sync, which is we collected a bunch of text that had different ways of saying something and what is the semantic destination of the menu where the system would take you. So for example here, there are two ways that the system knew of saying going to the route destination of directions. Directions or directions, please. You could imagine there are many more and examples like that. So what you do is you build a statistical language model, which we call Ngram, which has models the probability of seeing the next word given the previous two words. And we count all of the times that we see directions, that we see please, given that the previous word was directions, things like that. And we build an Ngram model. And then we also build an index. This is again going to the search case. In this case, the directions is kind of like a web page that contains these sentences. So it's trying to match in a fuzzy way. That's why search engines are robust, because they are not very strict. As long as they match something, they will return. That's the training phase. So even if you say something like directions, which doesn't match exactly, the recognizer here will recognize it because it's looking at engrams, which are much more flexible. You can recognize pretty much anything. It's not very rigid. And then you will say, you search, it's kind of like entering this query, directions into your search engine. It will match directions. This doesn't match, but it doesn't matter. It will find this web page that is the one that matches best. So this is a case where you can do understanding in a very different way. You're decomposing the problem into a dictation type problem followed by an information retrieval search engine type problem, which was quite successful. Let me skip this. So one of the things in building dialogue systems like that is you want to be less rigid. You don't want the user to be following directions of the machine. Nowadays, it's kind of like a robot. You want the user to say, well, how can I help you? And you just say whatever you want. This is called user initiative dialogues. If you can do it, it results in a shorter call. How many of you remember calling to a system and being in a voice menu hell, where it takes you forever until you get to the destination? I mean, it's kind of painful. Much better to say, well, this is what I want. You just say what you want quickly, and the system routes you to the right place. More natural, and it's particularly useful when you have many choices. And more of the technology is moving in that direction. The problem is that the first systems, a lot of the work in the first systems was done at AT&T back in 1990s, 2000, requires lots of PhDs. So what happened is that you could build it, but it was so expensive to build that you were not saving any money with the operators. Who do you pay, the operators or the PhDs? You know, that's the only question. And it could lead to user frustration, because sometimes the system appears more human than it really is. This is an example, pretty funny example of a case where frustration for those interested in emotion detection kicks in.
AT&T. I am an AT&T automated assistant. You can speak naturally to me. How may I help you?
I need help from a human being. I can't talk to a recording. This sucks. Give me a human being.
You can go ahead and speak naturally to me. I can understand your speech and help you get the service that you need. Just briefly tell me how I may help you.
Months ago, I called up and supposed to have gotten a service where I get 7 cents a minute. Well, I haven't got 7 cents a minute yet. They keep charging me 10 cents a minute. I want to talk to a human being and get this cleared up. I don't want to talk to a recording because a recording can't think for itself. I kind of doubt if a human being can, because they don't answer no more.
I can help you with that. Are you calling from your home phone?
Yes, I am.
I'm accessing your account. Please hold while I transfer your call.
So you can detect some frustration there. Not sure how you handle the call differently, but and that's because these systems are meant to be more intelligent, more human-like, but they are not quite there yet, right? Okay, this is an interesting case. So one of the first customers in deploying these interactive voice response systems, or IVR for short, at least in the United States, were the airlines. I don't know why, but they were. And typically, when you fly, and all of you probably have flown, many of you to come here, there's many stages. You have a new ticket, you booked, you existing, and lots of cases. And at each point, what you want, if you call the system, you're calling for a different reason, right? So could you leverage that? And that's kind of the question. So this would give you a very quick overview of the waveform if you were to call, a few years ago, United Airlines. This is the first time that the user could speak. So the first minute is like the user listening to a pre-recorded prompt that United Airlines had said, which includes things that will be familiar to you, such as, please listen carefully, our many options have changed. Well, I mean, yeah, it happens every time I call, so why do you need to tell me? You know, it just consumes 5 more seconds. And the thing that they tell you is, by the way, you should go and check our website first. Well, that's why I'm calling, because I checked it first and the answer that I wanted wasn't there, but I need to swallow that message. Then followed by fly the friendly skies, all their marketing. It's like, oh, just let me tell you what my problem is. It's like, I will spare you playing this back, but it's painful. So that's what a lot of customers hated, right? Northwest Airlines was shorter, still a long time. And then American Airlines was developed by Tell.me. And they did something interesting, and I will first play the prompt to you to see why it looked more intelligent. Oops.
Thank you for calling American Airlines, the only airline with more room throughout coach. We're glad you called. Our records show you on a 2:30 p.m. flight out of Washington Dulles today. But that flight has been delayed 2 hours because of heavy rain in the D.C. area. That means you'll miss your connection in Chicago at 5:05 p.m., but we rebooked you on a 6:50 flight out of Chicago that arrives in San Francisco at 9:23 p.m. Will that work for you?
Sure.
Great. You're on American Flight 47, departing Chicago O'Hare today at 6:50 p.m. Would you like to stay in an aisle seat?
So this is one example where not only is it better than all of these systems, it's actually better than many human operators. And why is that? Because this uses not just speech as an independent component. It uses a lot more knowledge. It's a lot smarter. Like if you call a random call center, they don't know you. They have no idea who you are, what you've done, have nothing. And you need to spend, even if you don't have to listen, you still need to listen to the marketing lingo. They couldn't get with the marketing guys even here. But even if you listen to all this with a person, it will take a long time for that person, the operator, to ask you all of the details about who you are and why you're calling before they can help you. But in this case, they integrated with the rest of the system. Through caller ID, they knew the phone number that you were using. They looked at them in their database. Oh, we have you. You're a customer. So I know that of the life of a cycle, you are not looking to inquire the fares. No, you already are a customer. You bought a ticket from American Airlines. Not only that, I look at the next record and say, oh, you're flying today. Why would customers call the day that they're flying? There's a handful of reasons. And one of them, typical, is maybe they're late and the flight was screwed up somehow. They can go and look at the flight, real-time information, say, yes, indeed, the flight was late. So the system already knows before, just because you call, that's all these things, it already knows you missed your connection. And it can predict with very high probability, why is it that you call? Because you missed your flight and you want an answer. So rather than asking you, tell me all the menu questions, just tell you, this is the most likely thing that you call for, right? And all you need to do is yes. So the speech recognition here was yes, no, which is a solved problem, basically. And there was a survey asked to all the customers of this system. And universally, they all said that the speech recognition was much more accurate than in the other systems. Even though that's definitely not true, because recognizing yes, no is very simple. And in fact, back then, the backend recognizer was identical in all of them. It was powered by nuance. But users thought that it was much more accurate. It's just not. What they thought is more intelligent. So it's not, speech recognition is part of the solution. But it's very important to know, in the grand scheme of things, what is the user trying to do? The solution may not be only speech. If you know a lot about why the user is calling, you can solve the problem much, much better. This is, again, another lesson of humility that we learned over the years. We think our technology is best. Well, sometimes there are other ways of solving the problem. And we should not fight them. We should embrace them. Because in this case, speech was helpful for yes, no. You just use it there. Why not? But the user experience is much better. Users started loving this kind of system. Let's see if I can show you a few videos before time's up. This is an example of multimodality. So someone was asking, well, we do the audio part and we do the video part separately. Wouldn't it make sense to combine them? And the answer is yes. And in fact, we started doing research back in 2000 in ways of combining systems, both the audio and the video signals or the graphics in a sense. This is one example.
Hello, my name is Kwan-San Wang from the speech group at Microsoft Research. What I'm going to show you today is a technology we developed here at Microsoft for humans to interact with computers in a more natural way. Specifically, the demo I'm going to show you today is what we call MyPad. MyPad is a personal information management application for mobile devices. Users can manage email, calendar, and contact lists using the graphical user interface, or GUI, in MyPad. In addition, MyPad understands naturally spoken commands. As a result, users can express their intent more freely and accomplish more sophisticated tasks. For example, a user can say, check email from Alex, received on Wednesday. As you can see, as soon as I speak, MyPad recognizes my intent and immediately takes appropriate actions. In this example, MyPad highlights the email items that match the search query that I wanted to look for. Many users have found it challenging in GUI to compose a conjunction query like the one I've just shown you, but they found it easy to do in speech. And speaking of natural, it is quite natural for users to introduce stuttering, hesitation, and other extraneous sounds like you know, and so on when they interact with computers. MyPad is programmed to deal with this fluency gracefully, as in the following example I'm going to show you. Schedule meeting with Alex Acero, Peter Mao, on Friday, on Monday, from 2 o'clock to 3 o'clock at Alex's office. The idea of MyPad is to let users express their intents naturally. For speech, that means combining the pointing device with speech in a multimodal scenario, as demonstrated in the following example. Send email to Kai-Fu, XD, Kwan-san. What I did just there is in the middle of my speech, I used a mouse click to separate the last email recipient from the previous ones. MyPad is capable of recognizing the meaning of the mouse click and integrated it with the rest of a natural understanding process. I hope this mini demo gives you a good idea of what kind of technology we are working on at Microsoft. Thank you very much.
So this video was done actually 2003, but the work was done in 2001. So we've known that multimodality can help at the research level. Of course, whether it's in a product or not, that's a different story. Let me skip this. This is another demo that we did, Dan Bohos did more recently, on using multimodality in a kiosk-like setting. So let me show you.
Hi. Thanks for coming to the triage kiosk. I'm in touch with the best doctors in the world. Are you here for your child or yourself?
Yeah, for my child.
So you recognize that there are two
So
people.
how can I help you?
He's been having diarrhea.
Oh no. Sorry to hear that. Hi there. What's your name?
She's looking at him.
And how old are you?
5.
So, 5 years old, right?
Look at, this is what the system sees. The two faces.
Okay.
And it's tracking.
Have you felt nauseous?
I don't know.
I'm sorry. Has your child been vomiting at all?
No.
Okay. So let's see. Has there been a fever?
Slight.
Have you been feeling tired lately?
Yes.
Let's see. How about abdominal pains?
He's not been complaining about.
Has your tummy been hurting?
Yes.
Oh, I'm really sorry. I hope it will feel better soon. Okay. Do you happen to know if your child has been losing weight?
No.
That's okay. Have you noticed whether your child's food looks funny? Is it black or darker than usual?
It is darker than usual.
Okay. Let's see. Considering everything you told me, I'd like to schedule an appointment with the doctor, just to be sure. However, not to worry, I'm not that concerned at this point. Can you bring your child to see the doctor this Friday at 10 a.m.?
Yes.
Great. Hope you'll feel better. And we'll see you then.
Yeah.
Bye-bye.
Bye. Thank you.
So this was motivated by the fact that especially in rural villages in India, they don't have enough health care. So it would be nice if they could build something like that. Let me show you this one. We've also thought for a long time that speech is a very good mechanism for input when you're driving, because you want to have your eyes on the road and your hands on the wheel. This is particularly true in Europe, where automatic transmission is not as popular and your hands are really busy. But even in the United States, it's illegal to drive while holding your device. So we had a project we call Commute UX that we worked on for the last 5 years or so. And this is some of the advances that we made from the research point of view.
So my name is Ivan Tashev, and I'm principal architect in speech technology group in Microsoft Research. We're in a driving simulator lab, and I'm going to demonstrate Commute UX. Commute UX is a next generation in-car dialogue system which allows you to say anything, anytime. This is a dialogue system which employs natural language input, and the system still will be able to understand you. Let's see how it works. At the beginning of our trip, let's start with listening to some music. Play track live for the party.
This is a life for the party.
Maybe you like this one.
So this was the classic way to listen to send a speech query, but we don't have to specify track or album or artist. Play Paul Simon. So as you can see, the system didn't need the clarification about the artist. Play The Submarine by the Beatles. And it can even understand not correctly specified names. Let's make some phone calls. My Bluetooth telephone is paired with the system, and the computer knows my address book, so I can ask directly by name. Call Jason Whitehorn.
Calling Jason E. Whitehorn, say yes or no.
Yes.
Jason E. Whitehorn, do you want cell, work or home?
Cell.
Calling Jason E. Whitehorn at cell.
So this was a classic and slightly painful way to interact with the Bluetooth phone, but our system can understand and doesn't need disambiguation if the name is unique. For example, call Konstantin at home.
Calling Konstantin Evangelos Lignos at home.
But there is even more. Frequently the driver needs to respond to some urgent text messages, and it's definitely not safe while you're driving. So we can use our speech input to do the same.
Message from Mom, ETA, say reply, delete, call back, or skip.
Reply. In 10 minutes.
Am I right that you log in 10 minutes?
or a number from the list.
Yes.
Got it. Message sent.
Maybe you notice it, but there is some irregularity in movement of our car, and I'm afraid that we have a flat tire. And because this is a rented car, I even don't know how to open the trunk. So now is the time to open the antique car owner's manual and to try to figure this out. But instead of this, our computer already did this for us. So we can just ask how to open the trunk. And we see the proper page here. But then we need to replace the flat tire. How to replace a flat tire. And we go directly to the page of the owner's manual, which describes how to replace the flat tire. Once we have our flat tire fixed, we can continue our trip and listen to some music. Play Norah Jones.
So we have this driving simulator, and by the way, it's very fun to use experiments. One of the things that we measure is how often the driver crosses the middle line. That is a symptom of like the level of engagement that you need from a driver. You don't want that to happen, right? So if you have to look at a touch screen, that happens all the time. And by the way, a lot of the companies that sell these driving simulators, they use it to determine driver fatigue, to determine whether you've drunk a little bit too much, these kind of things, right? But it's a very interesting research area as well. This is a prototype that one of the researchers in the team built to say, well, how can you combine speech and natural language with math? We know that from early this morning, some of our high school students, for instance, are not necessarily that bright. Wouldn't it be nice to help them with some technology? So let me show you. So she's typing down there an equation, and it comes in pretty print form up there. So now she's describing words what she wants. Take the log of 1. Wow, that happens. Or the base 2 log of 1. So the system knows.
Take the natural log of equation 1.
Or you can speak.
Multiply by x. Raised to the power of 5. X cubed minus 3x equals 2. Move 3x to the right side of equation 1. Add x squared to both sides of equation 2. Factorize the left side. Factorize the right side. X plus 3y equal to 1.
He made a mistake, speech recognition mistake, and she corrected it up there. So it's real.
X minus 2y equal to 4.
I think she's interested in solving a set of linear equations.
Multiply equation 2 by minus 2. Add equation 1 and equation 3. Divide each side of equation 4 by 7.
So whenever I show this, a lot of the people that ask me questions say, when can I have that? This was just a prototype. We were experimenting not just in recognizing the words, but doing the understanding. And oftentimes when students do math problems, for instance, it's not just equation after equation. They typically add some words. Like now they take the logarithm or factorize this. So you could use this not just for commanding the system, but to see if what they said and they do is actually consistent. Maybe you can detect that way where they made a mistake. We've had interest in education for quite some time. This is some prototype that we did back in 2007 to help students to learn how to read. So one of the things about reading is, well, the more you read, the better you will get at reading. How can we get more reading? Well, typically it's mom or dad helping. Come here, Joe, and read some more. Could you have a machine do something similar? Time on task. So how about a game? I mean, if you build like a little game, maybe we can do that. So this demo addresses this. So he needs to read Fight the Snakes. And if he reads it,
Fight the snake.
The guy kills the snake and moves on to the next. But sometimes he doesn't read.
Pull the door. Pull the door.
He's saying close the door instead of reading.
Close the door.
He's supposed to be reading, pull the rope, but he's not reading. So he gets killed. His character gets killed.
I said close the door.
Well, next time read.
Fight the snake.
Now he's getting better.
Pull the rope. Pull the rope.
Ooh, safe.
Would you like to play that game at home?
Sure. Yeah, I love it.
Let's see. Running out of time. Okay, so I think this is probably a good time to conclude. We're already over time. So this is, I was planning to give more details on this, but you know, we improvised, changed things a little bit around. But I hope that you got at least some idea, some demos, some directions of what are some work that you could do in research. There's plenty to do. A lot has been advanced, but there's plenty more to do. So thanks for being patient with me this morning. Thanks.